In this lesson, we're taking what you saw in the previous lesson about coordinate proof and taking figures and putting them in the coordinate plane, and now we're applying them to quadrilaterals. So a couple of reminders that some easy ways to place a figure in the coordinate plane are to use the origin as a vertex, or center the figure at the origin, or center a side of the figure at the origin, or if possible, use one or both axes as sides of the figure. So here they've positioned this rectangle with length 8 and width 3 in the coordinate plane as described. So they placed it this way. And notice how the length of the longest side is 8 and the shorter side is 3, and that's why the coordinates are as indicated. A different way they could have located it in the coordinate plane is to position one of the vertices at 0, 0. Notice how now this long segment is having this vertex at 8, 0, and so on and so forth. When we use the coordinate plane to do a coordinate proof of properties of figures, we use variables instead of numbers like this. So let us consider, if I have a square with side lengths 2a, how could I position that in this figure? So I could position it like this, and you'll forgive my bad drawing, but you get the idea. And this is 2a, and so is this. So what would be the coordinates of the vertices? Well, if I take this figure and copy it and paste it down here, well, if the length of this side is 2a, then this point is 0, 2a. And this one over here would be 2a, 2a. This point down here would be 0, 0. And finally, this vertex would be 2a, 0. What's another way we could have positioned the square? Well, we could have taken it and centered it, and in doing so, the coordinates would have been -a, a, this would have been a, a, coordinates down here would have been -a, a, and this point would have been a, a. and a common negative a. When writing a coordinate proof, why are variables used instead of numbers? Well, we use coordinates, or we use variables to show that the property is true regardless of the lengths or locations. So here we have example 1, part A, and we're using slope to write the coordinate proof that this figure is a parallelogram. And so you see, just like we did in lesson 1 of this chapter, we found the slopes of the sides, and we showed that there are two pairs of opposite parallel sides, and that therefore this is a parallelogram. Here they're asking us to use the distance formula to write that coordinate proof. So the first length we're finding is the length of AB. That's these 2 points. And so filling in this blank is 3 minus 4 quantity squared plus 1 minus 4 quantity squared. Remember, that's x minus x squared plus y minus y squared. So 3 minus 4 is negative 1 that they have squared here. 1 minus 4 is negative 3. And 1 squared is 1. Negative 1 squared is still 1. Negative 3 squared is 9, so this is the square root of 10. Finding the length of BC, I have negative 2 minus 3 and negative 1 minus 1. Simplifying this, they have the negative 5 getting squared. For the y's, I have negative 2 being squared. Negative 5 squared is 25. Negative 2 squared is 4. 25 plus 4 is 29. So the length of BC is the square root of 29. Continuing. CD now I'm finding, so that's these 2 points. That's negative 1, this negative 1, minus negative 2, and then 2 minus negative 1. Simplifying, negative 1 minus negative 2 becomes negative 1 plus 2, so that's where this 1 is coming from. 2 minus negative 1 becomes 2 plus 1, so that's 3. 1 squared is 1, 3 squared is 9, and there's my square root of 10. Just like up here I had square root of 10. Finally, the length of DA, that's 4 minus negative 1, and then 4 minus 2. Four minus negative 1 is 5. 4 minus 2 is 2. And when I simplify that, there's my square root of 29. Compare the side lengths. The lengths of the opposite sides are equal. So by the distance formula, we can conclude that ABCD is a parallelogram. Suppose you want to prove that a general parallelogram has diagonals that bisect each other. Why is it convenient to use general vertex coefficients such as 2a and 2b? In order to show that the diagonals are bisecting each other, one of the steps that you're eventually going to take is to find the midpoint. And so, since proving diagonals bisect each other would involve using the midpoint formula. Finding the average of values like 2a and 2b removes the prospect of eventually using fractions. So the purpose of the 2a and the 2b in a situation like this would help us avoid fractions, which we know tend to cause some grief in teenage students. In this your turn example, it's multifaceted. We're proving that this is a parallelogram. It doesn't say how, so let's do the easiest method, which in my opinion is to find the slope. All right, so slope of AB, remember slope is difference of y's over difference of x's. So my y values are 2 minus 2 that I'm dividing by 8 minus 3. And this is just going to equal 0. The slope of BC, this time I'm looking at this point and this one, same formula, y's over x's, so that's 0 minus 2 over 5 minus 8, and that simplifies to positive 2 over 3. Let me clarify, 0 minus 2 is negative 2 and 5 minus 8 is negative 3, but a negative over a negative simplifies to a positive. Slope of CD, that's these 2 points, y minus y over x minus x becomes 0. Notice how these two slopes are now equal. And slope of AD is 0 minus 2 over 0 minus 3. And once again, that's positive 2/3 when I realize that a negative over a negative becomes positive. So ABCD is a parallelogram because it has opposite parallel sides. In your turn 5, it's asking us to prove that the diagonals bisect each other. So probably the easiest way to do this is to find the midpoints of the two diagonals and show that they are the same point. So midpoint of AC, remember that's going to be average of x's, comma, average of y's. So that's going to be 3 plus 5 divided by 2, comma, and then I'm going to do the same thing with the y's. So taking this 2 and this 0, 2 plus 0 divided by 2, and that's going to equal 3 plus 5 is 8, 8 over 2 is 4, 2 plus 0 is 2, 2 divided by 2 is 1. So the midpoint of segment AC is 4, 1. Now I'm going to find the midpoint of BD, the other diagonal. So that's 8 plus 0 divided by 2, comma, y coordinates 2 plus 0 divided by 2. And once again, 8 plus 0 is 8. 8 divided by 2 is 4. 2 plus 0 is 2. 2 divided by 2 is 1. So since the diagonals intersect each other at their midpoints, the diagonals bisect each other. How would we prove that QRST is not a square? We could use distance formula. To show that all sides are not congruent. Or we could use slope to show that the diagonals are not perpendicular. In this figure, we're trying to classify the quadrilateral as a rectangle, rhombus, or square. So we're already told that it's a parallelogram. So in step 1, they've graphed it. Step 2, they're determining if it's a rectangle. Notice how? By finding the length of the diagonals and showing that they are not equal to each other. Since it's a rectangle, we know it's not a square. And then they used slope. Notice here, by finding the slope of the diagonals, they showed that the diagonals' slopes are opposite reciprocals, thus making them perpendicular. And remember that in a rhombus, the diagonals are perpendicular. So this figure is a rhombus. Same instructions, different points. Step 1, graph it. Step 2, they have us using the distance formula to determine if this is a rectangle. Myself personally, if these blanks weren't there, I would have used slope. I think slope is easier. But let's go ahead and fill in their blanks. So in order to determine whether this is a rectangle, they're finding the length of EG, so that's these 2 points in the distance formula. So they've got the 3 here minus -4, and then 0 minus -1. 3 minus -4 is 7. 7 squared is 49. 0 minus -1 is 1, and 1 squared is 1. So 49 plus 1 is 50. So I have the square root of 50. And what they're wanting you to realize here is that this square root of 50 can be simplified. You should have done this in algebra last year. It has a perfect square factor. In other words, 50 is divisible by 25 in this instance. So I can break this square root of 50 down to be 5 radical 2. Now let's find the length of FH. That's using these 2 points. So I have 2 minus -3, and then that's being squared, and -3 minus 2 being squared. So this is 5 squared, which is 25. This is -5 squared, which is still 25. So I have square root of 50 here, and that we already talked about how it is 5 radical 2. So since 5 radical 2 equals 5 radical 2, the diagonals are congruent. and EFGH is a rectangle. In step 3, they have us determining whether this is a rhombus. So they're doing that using the slope of EG and they've calculated it here, and then they found the slope of FH here. Notice that they are not opposite reciprocals, so EG is not perpendicular to segment FH, and that means EFGH is not a rhombus and therefore cannot be a square.